Okay, let's begin by revisiting where we left off last time. Some of the important conclusions from last time. We talked about how kx and ky are two vectors that can be used to describe wave functions. There's example wave functions with different values of k in the x and y direction shown here. 0 and pi over a are the simple solutions. And you can see how each of those corresponds to a different region of that Brillouin zone there. So that shows us how those wave functions map onto space, and the vectors shown on that unit cell for the square lattice there help you understand where those points are and what directions they correspond to in the crystal. We spent time talking about how curvature in those diagrams relates to the effective mass, and how effective mass is a free electron picture sort of terminology, but it tells you about how easily the electrons move between the atoms. It tells you if they are really localized on the lattice or if they can delocalize between the atoms. And we gave this example in graphene where the dispersion, or the E versus K diagram, has a linear relationship right where the conduction band and valence band meet. That point is called the Dirac point, and the idea here is that the slope being linear means that at the transition from the left side of that diagram to the right side of that diagram at the Dirac point, the curvature is infinite. And so if the Fermi energy sits right at the Dirac point and the curvature is infinite, then electrons at that point are massless. And the masslessness means that the charge transport mobilities are infinitely high. And so that is a really cool property of these diagrams. You can look at the lines where the Fermi energy is and say something about the behavior of electrons in the solid, graphene being a very cool example of that. All right, and then we started talking about optical spectroscopy in solids, and that's where I'm going to pick up again for today. You know, in a molecule, you see a band, a peak of some kind, and that corresponds to a resonant transition from one level to another, say the HOMO-LUMO transition, for example. And so that's the promotion of an electron across that spacing. There may be multiple different absorption bands that are visible for a molecule, but the point is here that typically you see an individual transition corresponding to one electronic spacing in the molecular orbital diagram. In a semiconductor, absorption of light can happen across many different transitions. The conduction band and valence band are made up of many molecular orbitals, very densely packed in energy. And so there are many transitions possible from the valence band to the conduction band. The minimum energy required to make that jump is equal to the band gap energy. And so the absorption spectrum of a semiconductor is shown on the right here, where the absorption onset is at the band gap energy. Below that energy, photons do not have enough energy to promote an electron from a filled state to an empty state. And so there's no absorption. But once you get to photons larger than the band gap, now there are many transitions possible, and the higher you go in energy, the more transitions are available. Okay, so there are many, many transitions accessible at energies greater than the band gap energy. And so we talked about how semiconductors, you have a wide variety of different materials, and they have a wide variety of gaps that span all possible gaps that fit a kind of semiconductor-like behavior. So from 3 electron volts, which is about what zinc sulfide or zinc oxide are, so UV absorbers out at 413 nanometers, all the way down to about 0.1 eV. 0.1 eV is a very small amount of energy. And that is equal to a 12,400 nanometer photon, which is out in the far IR. So semiconductors span that full range of energies, depending upon the material composition. So those absorption onsets can appear all over the electromagnetic spectrum. Remember an important value here, 1240 nanometers is equal to 1 electron volt. All right, so let's think about this a little bit further. When you promote an electron in a solid, let's say you use a 4 eV photon or a 3.5 eV photon to excite the semiconductor. The electron can come from many different levels. It can go to many different levels. The spacing will always be equal to the photon energy, but you can start down with electrons down at the bottom of the valence band or the top of the valence band. Many possible transitions can occur. Those charges produced by the photoexcitation have excess energy in them, and they're going to try and find their way back to the ground state. And the fastest thing that happens is typically cooling of the carriers. So the excess energy in the electron that's above the bottom of the conduction band, or the excess energy in the hole that is below the edge of the valence band, is lost to vibrations. So the electron falls down and the hole bubbles up. Heat is released. And that process is fast. It happens on a picosecond time scale. And then those charges sit there for a while. And over nanoseconds to microseconds, they stare at each other. And then eventually, the electron makes the leap across the gap, and you lose a photon of energy h nu. Okay, so that photon is, of energy equal to the band gap. So that photon, that jump that's emitted gives rise to fluorescence or photoluminescence, and the energy is the band gap energy. So when you look at the absorption spectrum and you plot the emission spectrum on top, the emission spectrum happens to be at the band gap energy of the semiconductor most of the time, not always. There are exceptions and important ones, but for the sort of simplest case, that emission feature is equal to the band gap energy. All right, so let's think about this using an energy versus K diagram. So on the left, you see the energy versus K diagram of gallium arsenide that we talked about before. Band gap here is 1.4 eV. The conduction band is more highly curved than the valence band. And we talked about this as being a result of the difference in the effective mass of an electron in a hole. Okay. And those two bands, the minimum of the conduction band and the maximum of the valence band, are both positioned at K equals 0. Okay, so the band gap spacing here is labeled on that diagram, and it corresponds to the K equals 0 point for the conduction band and the valence band. And this is very important because optical transitions need to conserve momentum. And so if you excite an electron into the conduction band and it falls down into the valence band, then the transition probability is related to whether or not momentum is conserved. So if you're at the same K point in that transition, so K equals 0 in this case, then the probability of emission is higher. And when the conduction band minimum and valence band maximum line up in this way at the same value of momentum, the semiconductor is said to be a direct band gap semiconductor. Direct band gap semiconductors have this sort of spectrum you see on the right. The absorbance turns on strongly at the band gap energy, and they are typically photoluminescent. And gallium arsenide is a very good example of that. You can make a really great laser out of gallium arsenide, for example, because of this property. Now, not all materials are like that. So here's an example, E versus K diagram for silicon. And you can see here that the conduction band is a little bit more complicated than the valence band. Okay, so in this diagram, conduction band has two minima that are not at k equals 0, and the valence band maximum is at k equals 0. So what's the band gap energy? Well, the band gap energy is not a function of k. The band gap energy is just the bottom of the bottom of the conduction to the top of the valence band. And if you were to plot this out in a density of states diagram, you wouldn't see all of this. You wouldn't see the k momentum information. And so that minimum spacing there corresponds to what's labeled with this arrow. Now, if you photoexcite silicon, say promoting an electron from here up to here, let's say promoting an electron from here up to there, the vertical transition conserves momentum. And then that electron, photoexcited electron, will actually fall down the diagram to the minimum here of the conduction band, and giving off phonons in the process, or liberating heat as it traverses momentum space. Okay. So now you have a photoexcited electron that sits at a momentum that is different than the momentum of the valence band maximum. And what that means is that the recombination, the transition where the electron falls from this position to that position, is very improbable. In fact, in order to conserve momentum and make this transition, you actually have to add a phonon to the mix. So that electron will react with the phonon in a way that allows the electron to transition from the conduction band to the valence band and recombine. But that probability is much lower as a result. And so silicon is not very photoluminescent. And the photoexcited states in silicon are very long-lived. Okay. Now, the fact that the conduction band minimum and the valence band maximum have different values of k makes silicon an indirect band gap semiconductor. Okay. So indirect band gap semiconductors have valence band maxima and conduction band minima at different values of k. And so the lowest energy transitions are improbable compared to higher energy transitions. So let's say you have an electron here in the top of the valence band, and you want to add a photon to it. One transition you can make is from the k equals 0 value for the valence band to the k equals 0 value in the conduction band. That transition is allowed and highly probable. The energy of that transition is larger than the band gap transition, which is this value of energy. So what you'll see with these types of semiconductors is that the absorption spectrum kind of reveals that. So here on the right, I've shown a hypothetical absorption spectrum for silicon. The band gap in silicon is about 1.1 eV. And so you're going to see absorption at that energy, but the intensity of that absorption is very low. Sorry, the y-axis here should not be energy in electron volts. It should be intensity or absorption units. So right at the band gap, the lowest energy spacing in the semiconductor between the filled and empty states, you see absorption, but it's very weak. Likewise, the photoluminescence is very weak. Probability of those two transitions are the same in essence. And so you do get some absorption, but not much. And then you go up in energy, and the number of transitions that have this indirect character goes up. And then eventually you get to an energy where there are direct transitions that can be accessed. Say, for example, the k equals 0 to the k equals 0 value, or maybe the k equals pi over 2a to the k equals pi over 2a value. So an indirect band gap semiconductor often has a region of low probability transitions approaching the band gap energy, and then a much higher energy region of direct transitions. Okay, so you can kind of see that in that spectrum here. Okay, so two types of semiconductors, and the conservation of momentum tells you about how probable the transitions are. So let's just take a look at this in terms of transition probabilities and transition dipoles. So optical transitions like this are linear transitions, and they involve a change in dipole moment from the ground to the excited state. And I like to think about this in terms of whether or not that transition couples to the oscillating electric field of a photon. A photon comes into the semiconductor that has an oscillating electric field, and if that electric field can couple to charge motion, then it will be absorbed. So people talk about the transition dipole moment as a measure of how much the ground and excited state that you're considering change in charge. Okay, and so I've diagrammed here two transitions, a direct transition and an indirect transition, for an energy versus k situation where you're going from a s orbital basis function at k equals 0 to a p orbital wave function at k equals 0 in the top case. So the k equals 0 to k equals 0 transition is a direct transition. And I've compared it to the k equals 0 to k equals pi over a transition in a band of s orbitals and a band of p orbitals. That's the indirect transition. Let's go find these over here on this diagram. Now, this E versus K diagram shows how the s orbital basis and the p orbital basis of the, say, the valence band and the conduction band in this material, how those energies vary with K. Remember that when K equals 0 for s orbitals, this guy right here, you start at low energy. And as you head toward pi over A, you build in nodes between the atoms and the energy goes up. For a p orbital, here's the k equals 0 solution for p orbitals in a sigma arrangement. That's the highest energy one. The pi over a is the lowest energy one, right? You flip the sign at each atom and suddenly you get a bonding orbital. So the p orbital basis at k equals 0 starts out at high energy and then it descends to low energy as you approach pi over a. So you can see that from the relative arrangements here in energy space. So now, if we take a photon and we want to promote an electron from here to there, or from here to there, we're talking about the k equals 0 to k equals 0 transition and the k equals 0 to k equals pi over a transition, which are diagrammed here as the orbital representation of the wave function. So you can look at the transition in terms of the orbital basis involved on a unit cell by unit cell basis. And so, if you look at the S crossing with a p orbital, you'll find that there's a transition dipole aligned in this way. So an S to p transition has a transition dipole moment. It is allowed. That is an allowed transition. And if you go from basis to basis to basis, you see all of those transition dipole moments lining up for k equals 0 to k equals 0. Now in this transition, the k equals 0 to k equals pi over a, you can see that the transition dipole moments of this combination is actually anti-parallel to this combination. And if you, boy, I got the signs of these guys wrong. So this should be pointing left, and this should be pointing right, and this should be pointing left, and this should be pointing right, and this should be pointing left. But the point is the same, I guess, in the end. The transition dipole moments change with the parity of the orbital, with the symmetry of the orbital here in this pi over a function. And because they cancel one another, there is no net transition dipole moment. And as a result, this thing is not allowed. It's electric dipole forbidden. Okay. Now, if you add a vibration in there and you move the atoms around, you can develop, that combination will give rise to a transition dipole moment, or can give rise to a transition dipole moment. But if you just look at the electronic basis functions involved, you can see how the k equals 0 to k equals 0 has this transition dipole moment and 0 to pi over a does not. And that helps to understand the difference between a direct transition in the top case and an indirect transition. A question. Thank you, Caitlin. All right. Now, all right, so let's just take a look at some more complete E versus K diagrams for some common semiconductors. Germanium, silicon in the middle, and gallium arsenide on the right. This is the kind of thing you'll see in a lecture type of a setting, often much more complicated than this. So let's analyze these three. So first go in there and see that the y-axis is in energy. It's in EV. The x-axis shows the L, gamma, and chi points for these three different crystal symmetries. These all have the diamond structure. Oh goodness, here we go again, running out of time. These all have the diamond structure. And so let's take a look now, find the band gap for each of these guys. So the band gap is labeled there as EG. And the spacing is from the top of the valence band to the bottom of the conduction band. So in this case, the top of the valence band is labeled as being 0, and the bottom of the conduction band is somewhere else. And that spacing is smallest for germanium, it's intermediate for silicon, and then it's largest for gallium arsenide. So silicon is 1.1, gallium arsenide is 1.4, and germanium is about 0.6 or 0.7, somewhere in there. And so you can see that pretty clearly on the diagram. The other thing you can see is that while the valence band maximum is always at gamma, the conduction band minimum is at different points. So it's at the L point in germanium, it's at the chi point in silicon, and it's at the gamma point in gallium arsenide. So the gallium arsenide case, so we just did these exact examples, but you can see that the direct band gap transitions, that only gallium arsenide has a direct band gap transition. So the band gap labeled there with EG occurs at the same value of momentum in the gallium arsenide case. Both are at chi. Silicon and germanium are, neither of them are direct. Both are indirect because the bottom of the conduction band is at a different value of K than the top of the valence band. If you want to stare at these further, you can try and understand the relative curvatures and the effective masses in germanium, silicon, and gallium arsenide, but it's not very obvious from these diagrams. So I'm not going to spend more time thinking about that. But in any case, that's how you look at these things, and you know, just by looking at that E versus K diagram, you can very quickly see things like, you know, the Fermi energy, the band gap, and decide whether or not the charges are going to be delocalized and have high charge mobilities. You can decide whether the probability of the transition is high or low, and whether or not the material is likely to be photoluminescent. So very, very powerful stuff. One more thing about this, actually, silicon and germanium are really nice materials for transistors and for photovoltaics. Photovoltaics are great because the photoexcited charges have really long lifetimes. You store a photon in silicon and germanium, and that exciton, or the photoexcited charges, live for a long time because the recombination of them by this luminescence process, jumping back down across the gap, is very improbable. Gallium arsenide, you excite an electron, and it does not live as long because it has a very easy time crossing the gap at the gamma point, okay, and undergoing luminescence. So silicon and germanium, good for solar cells. Gallium arsenide, good for lasers, LEDs, um, that kind of thing. All right. So just a few conclusions from this section. So the energy can be plotted uh, in reference to a direction in the crystal using the block functions and using treating K as a vector. And the various Brillouin zones that you get map onto the crystal lattices, and there's all these symbols for the various points there telling you about how K varies along that direction. Um, so near the conduction band minimum and valence band maximum, it's a reasonably good approximation that electrons behave like free electrons where their energy scales quadratically with momentum. And so people have developed language to talk about this, including this effective mass parameter, which tells you about how well the electrons behave in those materials, or how well they obey this free electron type of picture. It's really kind of a fudge factor for the free electron picture, and it tells you how much the electrons actually interact with the lattice, to what extent they are not free. And so people talk about light electrons, those having those sitting in bands with very strong orbital interactions that have high curvature. Charges are delocalized and move with high velocity. And so, and of course the inverse, heavy charges that sit in localized bands with poor orbital overlap and low charge transport mobility. So you can just pull that off of an E versus K diagram by looking at the curvature at one of those in one of those plots. And then the absorption and the emission properties also depend upon momentum, because momentum must be conserved in one of these transitions. So, you know, you want the K value to remain the same. And some materials, the conduction band minimum, valence band maximum, share the same momentum and make them direct materials, and others do not. And that changes, you know, what kind of characteristics they have, you know, what they're good for. All right, so now I want to begin talking about photoexcited states and excitons, and this is going to be our transition into talking about nanocrystals and building on the solid state physics that we've learned. So what is an exciton? An exciton is a photoexcited electron that is attracted to the hole that was produced upon photoexcitation. So I've diagrammed one down there on the bottom left. You know, you're used to seeing these transitions from valence to conduction band, but the product, those are two charged entities that are attracted to one another coulomically. So this gives rise to what's called an exciton binding energy, or the energy required to pull the electron and hole apart within the crystal. Okay, so this is another Coulomb type of a problem. And so the relevant quantities here are the dielectric constant of the material and the spacing between them. Now, the spacing between the electron and hole can be talked about using the Bohr model of the material, which we'll talk about here in just a moment. But the that spacing, which is labeled as RB star there, is the Bohr exciton radius, which is going to appear here on the right. So the size of the exciton, that Bohr exciton radius, is a very important parameter. And there are sort of two types of excitons that have very different behaviors, labeled as being Wannier excitons and Frankel excitons. Wannier excitons have a Bohr exciton radius, or a separation between the electron and the hole, that is greater than or much greater than the unit cell dimensions. And this type of a situation, you know, in that world, the electron and hole are very delocalized over many atoms. And that type of an exciton appears in semiconductors with large dielectric constants, so greater than 10, for example. And it gives rise to relatively weak binding of the electron and hole. So in the Coulomb picture, the further apart they are, the weaker the interaction, and the dielectric constant further weakens that. So the energy you have to pay to pull those kinds of charges apart is very small, 100 MeV or less. And keep in mind that at 298 Kelvin, room temperature, the thermal energy is equal to about 25 millielectron volts. And so, excitons that are more weakly bound than that, or less tightly bound than that, will dissociate at room temperature. So they actually don't bind in the semiconductor. They fall apart because thermal energy is enough to drive them away from each other. Okay. These types of excitons are typically larger than 2 nanometers in diameter. They can be 100 nanometers in diameter, which is very many unit cells. Frankel excitons, another class of excitons, they have much smaller exciton radii. So these are cases where the electron and the hole are very much more tightly bound to each other. And they appear in materials with small dielectric constants, organic materials, for example. So small dielectric constants, there's very weak screening of the two charges from one another, and this gives rise to much closer interaction, much more tight binding, 0.1 to 1 eV binding energy. So 1 electron volt binding energy is huge. That's a big energy penalty to pay to pull the charges apart. And you get Bohr exciton radii on the order of the size of a molecule, 1 nanometer or so. So organic crystals like rubrine kind of show this sort of thing. Pentacene has a Frankel exciton, but so do things like sodium chloride. If you excite sodium chloride, the charges are really localized. The orbital interaction strengths are very weak, and so the bands are flat. The effective masses are high, etc. All right. Yes, Salvador very smartly asks, can R be used for non-hydrogen atoms? This is a Bohr exciton radius, so let's talk about this for wait a second. Where is my slide? Oh, I defined it on this and I forgot to talk about it. Sorry about that, or maybe I did. Let's just back up and take a look at this again. So here I've talked to you, you can think about the electron and the hole orbiting each other in the material, okay? And it's sort of like an electron that's attracted to the nucleus of a hydrogen atom. So in this picture, the hole kind of behaves a little bit like the nucleus does. And so the Bohr radius of a hydrogen atom can be calculated from this equation shown here at the top of the page. You've got the dielectric constant of a vacuum up there. You have the mass of the electron, and then the elementary charges of those two things that are attracted to one another. Now, an exciton is a little bit more complicated than that because the two charges have similar masses. The mass of an electron is very small compared to a proton or the nucleus. And so in the hydrogen atom picture, you can ignore the mass of the nucleus and just consider it to be sort of fixed. In the case of an exciton, you have to consider both. And so you end up with a very similar kind of an equation, but in this case, the mass is not just the mass of the electron, but you use the reduced mass of the two charges. And in this case, the reduced effective masses of the electron and hole here. So 1 over the reduced mass of the electron plus 1 over the reduced mass of the hole. So this Bohr exciton radius is sort of very much like a hydrogen atom, where the two charges are orbiting around one another. A big difference is this reduced effective mass. And then the other is the dielectric constant. So in the case of the hydrogen atom, we have the dielectric constant of a vacuum. And in the case of a solid, we have some other number that is usually a lot higher. And so, the radius of the exciton is much larger than that of a hydrogen atom for those two reasons. Okay, so 1A excitons are large. They form in inorganic crystals with high dielectric constants, and delocalized charges in bands that are strongly interacting. Frankel excitons in organic crystals and in materials where the bands are sort of flat and charges are heavy. All right, so let's now start talking about what happens if you look at a photoexcited state in a semiconductor crystal that is smaller than the Bohr exciton radius. So I've put this cartoon up here of a semiconductor nanocrystal that could be gallium arsenide, for instance. And I've drawn this representation of the exciton on top of it and shown how the crystal may actually be smaller than the preferred Bohr radius of that exciton. So what happens when that occurs? You end up in a situation which is referred to as spatial confinement of the excited state. Okay, so of course the charges can't really leak out of the crystal. All the basis functions and the orbitals in which they live are within the lattice. And so the lattice truncates those wave functions. And it was recognized that you can talk about this sort of behavior much like you would talk about a particle in a box that you learn about in quantum mechanics. So the dimensions of the crystal sort of define an infinite potential well in which the wave functions can exist. Okay? So we'll go and talk about how that plays out in just a moment here, but bear in mind that there are different regimes of this kind of confinement. There's very strong confinement, where the diameter of that crystal is much smaller than the Bohr exciton radius. And then there's situations where the diameter is larger than the Bohr exciton radius, or similar to that Bohr exciton radius. And that's sort of talked about as being weak confinement. If the crystal is 10 times larger than the Bohr exciton radius, then the excitons are not really confined, and it just behaves like a small piece of bulk material from a quantum mechanical point of view. All right, so confinement does a couple of things. One is it increases the spatial overlap of the electron and the whole wave functions, and this makes the two charges bind more tightly to one another. And it also changes the kinetic energies of those wave functions. Okay, so the particle in a box picture that we're going to talk about addresses the kinetic energy piece. So take there's your sort of standard particle in a box, infinite potential well that is bounded by this dimension here, this dimension x. And in our example, x can be 0 on the left side of the box or as large as a, the right side of the box. And so if you have a generic wave function here, block function, for example, for the wave function as a function of x, you get e to the ik and a, where a is that unit cell dimension, and n is a quantum number, an integer multiple of the different possible wave functions. Now, this picture, it is useful because the wave function has to decay to 0 at the edges of the potential well. So psi must be equal to 0 when x is equal to 0 or when x is equal to a. And if you set that boundary condition, only particular values of the k, the quantum number, actually satisfy that condition. Okay, and it's really integer multiples of pi over a satisfy that condition. So let's take a look at what those look like here on the next slide. So here are 4 different integer multiples of the solution, 1, 2, 3, 4, and each of those different wave functions has a different value of k. Pi over a is one of them, and so on, going up in energy with this quantum number 1, 2, 3, 4. Okay, and you can see how the wave length for the lowest energy one is longer than this one, than that one, than that one. So you add increasing numbers of nodes as you go up in energy, like you have all learned. So the energies of these different wave functions can be expressed this way, where you take the integer multiple of the function of interest and the dimensions of the box and the mass of the electron, and you can calculate what those energies are. And you'll see that the energies go with 1 over a squared. So the energies depend upon the dimensions of the box. If you make the box smaller, the energy goes up as 1 over the dimension squared. Okay, so the kinetic energies of these wave functions you see here are a strong function of the dimensions of this infinite potential well. So in the case of our nanocrystal, the wave functions in the nanocrystal are bounded by the dimensions of the crystal. The smaller you make the crystal, the larger the kinetic energies, the greater this confinement energy. Now, Lou Bruce, let's see here, before we get to that, let's take a look at another picture of this thing and see how it relates to the free electron picture. So we showed you this diagram here for E versus K, and at the bottom of the band, of the conduction band, E versus K is quadratic with K, okay? And that's very much the same in the particle in a box picture. But now there are only specific solutions that are possible. So you can think about this band here of possible solutions as having many different values of K, many different values of momentum possible. The larger the momentum, the larger the energy, and it goes with K squared. But there are an infinite number of possible values of K, infinite number of possible velocities for the electron. But that's not true in a quantum confined situation where you have an infinite potential well and the wave functions have to decay to 0 at the edges of the well. There are specific wave functions that are possible, and they're separated in space as indicated here by these points, okay? So only discrete levels are possible now. Instead of a continuum of momenta, you have discrete values of the momentum that can be accessed when you apply this quantum confining potential, okay? So what that does is it takes a semiconductor with an infinitely dense band structure and makes it molecular, where you have these particle in a box type energy levels. Now, Lou Bruce, a faculty member in our own department, he recognized this and he formulated a theory to describe the band gap energy in a semiconductor, which is affectionately referred to as the Bruce equation. He said, all right, so if you want to know the band gap of a semiconductor that is quantum confined, you have to start with the band gap of the bulk material, add the confinement energy, which is this kinetic energy piece, and then you also have to consider the changes in the Coulomb potential or the attraction of the electron and the hole to each other, the binding energy of that electron hole. So he took each of those 3 parts and he solved the individual components. The bulk value is something that's given by the material. The confinement energy is defined as we talked about previously. So h bar squared over mu squared times the radius or dimension squared. So r here is the radius of a spherical well or a nanocrystal, for example. And then the last piece, the minus 1.8 q squared over epsilon r, that's the Coulombic potential. So he just took some of the symbols out of there and replaced them with a constant, which is, the same as calculating it out expressly. So each of those pieces you can see broken out there in this nice equation. And what Bruce also recognized is that that middle piece, the confinement potential, goes as 1 over the radius squared, whereas the Coulomb component is 1 over r. And in a strongly confined situation where the box is very small, that radius is small. And so as the radius of these crystals gets smaller and smaller and they transition into this confinement regime, this r squared term begins to dominate. And so you get different band gap energies in a quantum dot because of this confinement effect. And it goes as 1 over the radius squared largely because the changes in the kinetic energy dominate on that length scale. Okay. So Lewis has a good chance of winning a Nobel Prize for this work, which I think was published in the Journal of Physical Chemistry. Lewis always says publishing in the Journal of Physical Chemistry is a perfectly good place to put forward your work, and this paper is certainly evidence of that, having been cited thousands of times at this point. All right, so Lewis considered one of the founders of this area of quantum confined semiconductors and nanocrystal science. All right, so let's take again another look here at the E versus K diagram. I've shown, there's another typo, the number of states plotted in energy versus momentum on this free electron picture, this quadratic curve there on the left. And the quantum confinement process in the sort of typical band diagram actually looks like what you see on the right. As you go up in energy, as you go to higher and higher values of this integer multiple, the spacing between levels actually starts to fall. Okay, and so eventually you get back to a situation where you get a continuum of electronic states. But near the bottom of the conduction band in this example, you get discrete spacings between the kinetic energies that are large enough to see individual levels. So a semiconductor with a continuum of states in its conduction band, as you begins to develop these localized, well-defined and well-separated molecular orbital states right below the conduction band edge, or equivalently right above the valence band edge. Another interesting thing is that the effective mass plays out very neatly here. So take, for example, the semiconductor on the left. Here the conduction band, E versus K, the conduction band in that E versus K diagram is much more strongly curved than the one on the bottom, and that's a consequence of the orbital interaction being stronger and the effective mass of the carriers in the conduction band being much lighter. Whereas in the valence band, the broadening in the band is not as pronounced. The charges are heavier. And you can see if you just take discrete values of K, that the orbitals that are possible in those bands, the only orbitals possible, are spaced differently in the conduction band and the valence band. So the valence band spacing and energy is very small. The conduction band spacing and energy is much larger. So if you look at those discrete levels there on the right, plotted as just molecular orbitals, you can see down there the valence band values are very tightly spaced, and the conduction band ones are not. The other interesting thing that happens is that the other thing you can see there is that those lines are often given quantum numbers. So these are like different quantum numbers for the hydrogen atom, and they're given these sort of generic S and P terms, one for the valence band and two for the conduction band, and so on. All right, so effective masses and the curvatures in the bands, the band widths, give rise to differences in the spacing of the various levels that you see there. So let's take a look at a real example here. So this is a figure borrowed from Munji Bawendi's paper. Chris Murray and Cherry Kagan and Munji wrote this. Let's see if I can, oops. Okay. They wrote this wonderful article, Annual Reviews of Material Science, showing how the optical spectra of these semiconductor quantum dots, or quantum confined cadmium selenide nanocrystals, how they vary with the dimensions of the nanocrystal. And so on the very far left, you see the E versus K diagrams For for cadmium selenide, the conduction band, there's one conduction band level shown, and there are three valence band levels shown. And then you can see that there are discrete values of K that are possible, formulated by those dots in the drawing. And there are transitions labeled there also from that conserve momentum. So from the same value of K in the filled to the same value of K in the empty. And they say, all right, as you go to smaller and smaller diameters, the spacing in K spreads out, and that gives rise to a larger spacing in energy of the various transitions that you can have. And also the lowest energy transition that's possible gets wider. And so a lot of time has been spent showing how this sort of phenomenon plays out in the optical spectrum of these materials. And just to the right of those diagrams, you can see a bunch of different UV visible absorption spectra of cadmium selenide, starting at the bottom down below 20 angstroms or 2 nanometers of diameter, and then heading up to as high as 15 nanometers in total diameter. And so not only do the peaks shift from left to right as the confinement potential gets smaller and smaller, the radius of the box, the dimensions of the box get larger and larger. The lowest energy thing shifts to the right, but also the spacings between the bands decreases as you get to larger and larger dimensions of the box. And I like this sort of stack of many, many spectra on top of each other, because you can see the individual transitions and how they evolve in energy as you go from one size to the next. And so each one of those little bumps there corresponds to a different transition in this E versus K diagram there on the left. Plotted on the right is the same data, now plotted in energy units on the bottom instead of wavelength. Okay, and then on top of that is plotted the photoluminescence spectra of all these materials, and you can see that the photoluminescence is also shifting as you change the radius of the crystal from a small crystal to a large crystal. It's red shifting, going to lower values of energy, which is longer wavelength. Okay, but in all cases, you can see that the photoluminescence spectrum sits right at the absorption onset for each of these materials. You can also really clearly see that the absorption onset for these materials is actually just a peak that has a characteristic width. And that peak is the homolumo transition, so to speak, in these molecules. It's this arrow here on this diagram, or this arrow here on this diagram. It is a resonant transition like you would have in a molecular system, and it's spaced out from the next nearest transition well enough that you get these big gaps between the various bands. So here's the lowest, there's the next, and so on. And as you go to higher energy, the spacings get smaller. Okay, so you can see all of that. The photoluminescence sits right on that homolumo transition. It's all very neat and tidy, like you would predict from the Bruce equation. All right, so let's take a little bit closer look at some of this. Excuse me. What time is it here? 12:40. Wow. So we're going to start talking about the radial distributions of electrons and holes as we go forward here. And I just wanted to remind you guys of what a radial distribution function is. So, you can think about a 1s electron as having this sort of wave function shape, where the wave function decays to smaller and smaller amplitude as you go to larger and larger radius. And right at the nucleus, here you have maximum amplitude of the wave function. So a very simple isotropic sort of a shape. People also talk about the probability distribution or the orbital representation rather than wave function representation. And for an 1s electron, that's a pretty simple result. You just multiply this curve by itself, and you get another one that's a little bit steeper. These things are not as useful for looking at differences between different charges in a semiconductor. And so people will often plot what's called a radial distribution function instead of a wave function. And the radial distribution function just takes this psi squared representation of the electron and multiplies it by radius squared. And what that does is it weights the longer distance data more heavily. It allows you, a good way to talk about this is that this y value is the probability of finding an electron in a shell surrounding the nucleus, for example, or the hole in an exciton. It's a probability of finding that electron at a spacing of r, in a shell of a spacing of r. Okay, so you picture a shell around the nucleus that has a radius of r, and you shrink that shell. Now you're getting closer and closer to the nucleus. The amplitude of the wave function is going up and up, but the shell is getting smaller and smaller. And so in these plots, what you find is that you have a peak and then it drops off as you get to the nucleus, because right at the nucleus where the radius is infinitely small, the dimensions of the shell are infinitely small. So you get these peaks. In any case, this is a much more powerful way to visualize electrons and how they distribute in atomic systems, but also how excitons distribute in nanocrystals. So here are two example radial distribution functions on the left and on the right. On the left, we have a radial distribution function for an electron. And on the right, we have, an electron in cadmium sulfide. And on the right, we have a radial distribution function in indium antinomide. Okay. And so I've given you there a couple of very useful numbers, which we're going to talk about in just a moment. But first, let's take a look at just the shape of this radial distribution function to think about what it means. So on the left-hand side, what you see is a shape that sort of goes up and comes down, much like what you saw on the previous slide, until you run into 4 nanometers. 4 nanometers is the edge of this hypothetical nanocrystal that we're discussing here. The wave function cannot go beyond that edge. That's your infinite potential well. And so the radial distribution function continues until it hits that value, and then it plummets, okay? But the shape of this curve is actually very similar to the shape of the radial distribution function of an electron in a piece that's not quantum confined. All right. So now let's take a look at indium antinomide, and you can see that the distribution function goes up, and then right at 4 nanometers, it's very abruptly cut off. Okay, it doesn't have this nice smooth shape anymore. It gets cut off somewhere here when it runs into the edge of this hypothetical 4 nanometer crystal. So why are these two materials different? Well, it has to do with the dielectric constant and the effective masses of electrons in that semiconductor. So cadmium sulfide has relatively strong bonding between the cadmium-based orbitals, and the effective masses are relatively light. And so the electrons are fairly delocalized. The dielectric constant is relatively high. And so what that means is that the charges are screened from each other, and the Bohr radius of the exciton is reasonably large. So, 2.5 to 3 nanometer exciton Bohr radius is a relatively big dimension. Now, this crystal radius is 4 nanometers. So 4 nanometers is larger than the Bohr exciton radius, but not by much. Okay, and so the crystal, the exciton here, as shown by this distribution function, does get truncated by the edges of the crystal, and I think I would call this an example of weak confinement. Now, in indium antinomide, on the other hand, the effective masses are very much lighter. You're down to 0.015. So the bandwidths in these semiconductors must be very large. The curvature must be very high. And then on top of that, the dielectric constant is double what it is in cadmium sulfide. Okay, so screening of charges is much greater in that case. And the radius is much, much, much larger in indium antinomide as a result. So excitons in indium antinomide are much more spread out. The electrons are much lighter, faster moving, and the charges are much better screened from each other. So an exciton in indium antinomide is large, and it's very weakly bound. An exciton in cadmium sulfide is relatively strongly bound as far as excitons go, and it's not too large. Okay, so you can see that I've been saying exciton this whole time. These plots are for the electron potential. Okay, you can make the same plot for the hole potential, which is slightly different because the mass of the hole is not the same as the mass of the electron. Okay, in any case, we'll do that soon. You can see very neatly how excited electrons in these two materials vary differently. So now let's take a look at the change in the conduction band energy as a function of diameter. So I plotted this confinement energy for the electron in cadmium sulfide and in indium antinomide here. As you change the diameter of the crystal, you're going to get different degrees of confinement in these semiconductors because the indium antinomide one, the sizes of its charges are much greater. Exciton Bohr radii are much smaller. Looks like I have I've copy and pasted the values of indium antinomide next to cadmium sulfide here. In fact, the mass of the electrons are higher in cadmium sulfide. The excitons are, the dielectric is smaller and the Bohr exciton radius is smaller, like was shown in the previous slide. And so what that means is that as you change the dimensions of the crystal, the energies that you get vary, and they vary to different extents. So the increase in energy happens at much larger dimensions in indium antinomide than it does in cadmium sulfide. Cadmium sulfide, you got to get all the way down to 10 nanometers or less. Indium antinomide starts to showing effects around 25, maybe 50 nanometer size pieces. Relatively large pieces of indium antinomide still display confinement characteristics. And that's all about this effective mass of the carrier, you know, how spread out they are and how well the two charges are screened from one another. Okay, so these curves are, it tells you that the importance of quantum confinement is material dependent for reasons that we have been discussing at length. All right, so that's what I have to tell you about confinement for today. You know, the excited electrons in a semiconductor are attracted to holes, and this leads to excitons. And the binding of those two carriers is really a Coulombic type of a binding. So it depends upon the dielectric constant, but it also depends upon the masses of the electrons in holes and how far apart they are. So excitons with large radii form in high dielectric materials with low effective masses and dissociate readily at room temperature. Most inorganic semiconductors fit this description. You know, the size of that exciton can be described by an exciton Bohr radius. And that Bohr radius is very helpful when thinking about confinement. You know, the dimensions of the crystal need to get down to that radius or slightly larger than it before you're going to start seeing any quantum confinement, and different materials will have different responses as a result. All right, so let's see here. So that's what I have to show you for today. As I mentioned, the website has been updated and I will take another look at it today and improve it further. Does anybody want to take an opportunity to ask any questions about your literature reviews or about the material thus far or where we're headed? Okay, so uh yeah, I'm going to go update the next reading to make sure that we're all on the same page. Take a look at what's there. Just do that right now. Yeah, so the Bruce review in physical chemistry and this synthesis paper. Um, those are the two things that we should be reading right now. So this is basically up to date. This one I don't think we're going to do, this Nate Lewis paper, and we'll probably transition to these afterward. But I'm going to sit down and work through that and let you know. All right, gang. So if you have any other questions, don't be afraid to reach out, and I will see you next week with another literature review. Thanks, guys.